Kia ora and welcome to this comprehensive course of Layer of Protection Analysis or LOPA. I'm your expert guide, and over the next two modules, which are the part of this single video, we will unpack the powerful tool used in the process safety and the risk analysis. Have you ever wondered how industries manage the immense risk associated with the hazardous chemicals and processes? How do they decide when safe enough truly is safe enough? LOPA provides a structured, quantitative answer to these critical questions. LOPA is a simplified form of quantitative risk assessment. Imagine it's a magnifying glass that helps us scrutinize potential accident scenarios one by one, focusing on how different proactive measures safeguards against harm. It's a key tool for estimating risk and determining if enough protection layers are in place to meet predefined safety goals. Throughout this course, we will follow a single compelling example, an uncontrolled exothermic reaction leading to overpressure in a chemical reactor vessel, demonstrating LOPA application step by step. Get ready to enhance your risk analysis expertise. LOPA isn't a new concept, but rather one that has evolved significantly, driven by the industry's need for consistency. Its origin lies in the desire to answer key questions about process safety using a rational, objective, key-based approach. Historically, decisions on protective layers were sometimes subjective or based on who shouted loudest. This led to a critical need for a more systematic methodology. The foundation were laid in late 1980s with the Chemical Manufacturer Association Responsible Care, a process safety code for management practices, which emphasized significant layer of protection. A pivotal movement arrived in 1993 when Center of Chemical Process Safety or CCPS published a guideline for safe automation of chemical processes. This document first suggested LOPA as a method to determine the integrity level of the safety instrumented functions or SIFs. The foundational CCPS layer of protection analysis simplified process risk assessment in 2001 cemented LOPA popularity, establishing its streamlined risk assessment tool for the entire industry. Subsequent CCPS guidelines, such as the Guidelines for the Enabling Condition and the Conditional Modifier, published in 2013, and the Guideline for Initiating Event and Independent Protection Layer, published in 2015, have further refined the methodology, providing more detailed guidelines and numerous examples. This continuous evaluation ensures LOPA remain a robust and a relevant tool for a process safety professional globally. At its heart, LOPA simplifies complex risk scenarios into three main components: initiating event, independent protection layers, and the consequences. Think of it like a chain of dominoes, where an initiating event is the first domino failing. Each subsequent domino is a protection layer designed to stop the chain. If all protection layers fail, the consequence occurs. An initiating event is the device failure, system failure, external event, or an improper human action that begin a sequence of events leading to one or more undesired consequences. It is the spark that ignites the potential hazard. For our continuous example, an uncontrolled exothermic reaction leading to a reactor overpressure, our initiating event is a loss of cooling water to the reactor jacket. Independent protection layers, IPLs, are safeguards that are truly independent from any initiating event and other IPLs, and are capable of preventing the scenario from proceeding the undesired consequence if they function as designed. They are the safety nets in our domino chain, catching the failing hazard. We will delve deep into IPL in later topics. Finally, consequences are the undesirable outcomes of the incident scenario. In LOPA, we are interested in the severity of these outcomes, whether it is an uncontrolled release, a fire, an explosion, or most critically, human injury or fatality. For our reactor, the ultimate consequence could be a reactor overpressure leading to rupture and release of hazardous material, potentially causing fatalities. Understanding these core elements is the first step to mastering LOPA. Crucially, LOPA isn't a tool for identifying new hazards. It's an analysis tool used for predefined scenarios. It typically builds up information from the qualitative hazard evaluation like HAZOP studies or what if analysis. These initial studies pinpoint potential danger and their causes. Once identified, a scenario in LOPA focuses on a single cause consequence pair. This singular focus is critical for clarity and consistency in analysis. Let's reiterate our continuous example scenario for LOPA. The scenario title would be Uncontrolled Exothermic Reaction Leading to Reactor Overpressure, and the description, a batch reactor experience a runaway exothermic reaction due to the loss of cooling water, potentially leading to overpressure, rupture, and release of hazardous material, causing injuries and fatalities. LOPA follows a structured step in scenario development. This often involves filtering scenarios based on the severity of the potential consequences. Our chosen scenario with the potential for a rupture and fatalities would undoubtedly be a candidate for the LOPA due to a high demand and the high severity. As described, we have selected the uncontrolled exothermic reaction in the reactor. Remember, LOPA is applied to one cause consequence pair at a time. For our example, the initiating event is loss of cooling water to the reactor jacket. The frequency of this event is then estimated, typically on an annual basis. This isn't just about a pump failing, it's about the frequency of any event that could lead to cooling loss. We will discuss frequency in more details in the next topics. Effective scenario development is the backbone of robust LOPA. It ensures that the subsequent analysis is focused and relevant. The initiating event frequency (IEF) is critical input for LOPA, representing how often an initiating event is expected to occur. These frequencies are usually expressed as event per year. It is absolutely essential to use consistent frequencies across an organization to ensure compatibility and reliability of your LOPA results. For our continuous example, loss of cooling water to the reactor jacket, how do we determine its frequency? CCPS guidelines provide suggested frequencies for common initiating events. These generic values are based on the extensive industry experience and compiled data. For instance, a basic process control system (BPCS) instrument loop failure, which could directly lead to the loss of cooling control, might have an generic IEF of 1 e to the power minus 1 events per year. However, generic data should always be used with caution. You must carefully consider if the data is acceptable to your specific process condition, your plant's unique maintenance practices, and its historical performance. Factors like extraordinary design, enhanced maintenance regimes, and human error reduction measures like key lock systems can significantly influence the actual IEF for your facility. Key data sources for IEF includes expert judgments and consult acknowledged experts in the field, utilizing published industry database and reliable handbooks, employing mathematical models and predictive techniques to estimate failure rates. Also, analyzing your own plant historical performance and maintenance records, often considered the most relevant. The overarching goal is to select a reasonable, often conservative best estimated value while always acknowledging any inherent uncertainties. For our reactor example, let's assume, based on the typical industrial data, an IEF of 1 to the power minus 1 per year for the loss of cooling water due to the BPCS control loop failure. This means, an average, this specific initiating event is expected to occur every once 10 years. The final outcome of a LOPA scenario is the consequence, representing the undesirable impact if all protective measures fail. This is where we consider the so what of the event, moving beyond just for the failure of its ultimate impact. Consequences can range from minor equipment damage to a significant environmental impact, most critically, human harm. There are typically four approaches for evaluating consequence severity in LOPA, each with varying level of details and rigor. The first one is the release magnitude. This approach estimates severity based purely on the type and quantity of material or energy released. While simple, it might not differentiate impact effectively across different facility locations. For our reactor, this could simply be a large release of hazardous material. The second category is the qualitative categories for the potential loss and harms. Here, impact is assessed using predefined category like potential for severe injury or fatality. This approach often uses conservative assumption. For instance, assuming 100% ignition probability for flammable release, our example for overpressure could classify it as a category 5 for potential for injuries and fatalities. The third one is the qualitative or the order of magnitude with conditional modifier. This is more refined approach where explicit probabilities are included for post-release event. This means accounting for factors such as probability of ignition or probability of personal presence after the release. This method tends to lead to a more estimate risk value, avoiding overestimation. We will explore conditional modifier in the later topics. The fourth one is the quantitative impact with the conditional modifiers. This is the most detailed and the rigorous approach, often utilizing full quantitative risk analysis QRA tool for complex dispersion modeling, blast effect analysis, and precise impact assessments. The chosen approach for the consequence evaluation must be consistent with your organization risk criteria. For our reactor overpressure scenario, let's consider the potential for fatalities or multiple severe injuries. We will continue this in our later topics where we will apply conditional modifier for a more nuanced assessment. That concludes our first module of this topic. We have introduced LOPA purpose, its evaluation, and the core elements of the initiating events, consequences, and scenario development. We have also set the stage with our continuous example, the uncontrolled exothermic reaction in a reactor vessel. You now have a solid foundation in the basics of LOPA, understanding how scenarios are defined and how their initiating events and potential consequences are evaluated. In our next module, we will dive deeper into the protective measures, the independent protection layers, and the conditional modifiers, and show you how LOPA empowers robust quantitative risk-based decision making. Get ready to build on this foundation and truly master LOPA. Welcome back to the next module of our LOPA course. In the earlier topics, we introduced IPL as a crucial safeguards. Now let's explore them in depth. An independent protection layer is more than just a generic safeguard. It is a device, system, or an action that can independently prevent an initiating event from escalating to a specific loss event or impact if it functions as designed. The independence is paramount, ensuring that the IPL effectiveness is not compromised by initiating event or the failure of another layer. An IPL must also be effective in its function and auditable to assure its perform as required throughout its life cycle. IPLs are quantitatively measured by their probability of failure on demand, PFD. So a PFD of zero point 0.1 means that there is a 10% chance it fail when needed, offering one order of magnitude of risk reduction. A PFD of zero point zero 0.01 is 1% chance, representing two orders of magnitude reduction. We will talk about this in more detail in a short while. IPLs can be broadly categorized as number one, passive IPLs. These do not require an active change of state or human action to achieve their function, provided their design and construction are correct. For example, dikes, blast wall, or flame arresters. For our reactor, a rupture disk could serve as a passive IPL, specifically designed to open as a set of overpressure, preventing catastrophic failure. The second one is the active IPL. These require movement from one state to another or a signal to take action in response to the process deviation. Example includes safety instrumented system or a pressure relief valves. A safety instrumented system loop like an automatic shutdown system for a runway reaction would be a key active IPL. The third one is the human IPL. Operator action can be credited as IPL, but only if they meet strict criteria regarding clear procedure, adequate training, sufficient response time, and a favorable human factor conditions. An operator response to a high temperature alarm to shut down the reactor could potentially be a human IPL. It is crucial to avoid double jeopardy, means you should not count the same risk reduction factor multiple times for the same scenario. For example, if an operator response relies on the BPCS alarm and the BPCS failure is the initiating event of that scenario, the operator response cannot be credited as an independent protection layer because the common component BPCS has already failed. For our continuous reactor overpressure scenario, after a loss of the cooling water, let's consider these potential IPLs. The first one is the operator response to high temperature alarm. Let's assign PFD of zero point 0.1 based on the typical operator action reliability and ensuring a clear procedure and adequate time for the response. Then we have a pressure safety valve. A correctly sized and a maintained PSV could have a PFD of 0.01. Safety instrumented function to open vent valve as a part of the sys. This would be a highly reliable automated system and potentially achieving a PFD of 0.01 for a SIL 3. Remember, IPL are the core of the risk reduction in LOPA. Each must be truly independent and reliably maintained throughout its life cycle to ensure the claim PFD is valid. LOPA allows for the further refinement of the risk calculation through the judicious use of the enabling condition and the conditional modifier. These are the probabilities that either enable the scenario to occur in the first place or modify the likelihood of a specific consequence after the release. An enabling condition is a condition that must be present or active for the scenario to proceed to a loss event. But it's neither a failure nor a protection layer itself. It represents a probability associated with the pre-release part of the incident sequence. For example, if our exothermic reaction in the batch reactor only poses an overpressure risk during the specific exotherm phase of the batch, then the probability of the reactor being in the vulnerable phase when the cooling is lost would be an enabling condition. Let's assume this is a critical phase occur for 50% of the total operating time of the reactor. So our EC probability might be zero point 0.5. Conditional modifiers, on the other hand, are probabilities generally associated with the post-release part of the incident sequence. They account for factors like probability of the ignition, probability of the personal presence in the affected area, or the probability of the fatal injury, given that release has occurred. These are particularly crucial when organization risk criteria are based on ultimate impact, such as fatalities, rather than simply in the occurrence of the release. Using conditional modifier can prevent overly conservative risk estimates by providing a more realistic based estimated values. For our reactor overpressure scenario, assuming a rupture and a release of the flammable material occurs, let's consider these conditional modifiers. What is the chance the released material ignites upon release? This can be estimated based on the material properties, for example, flash point, LEL, release conditions, and the presence of the potential ignition source in that area. For a large flammable release, let's assign probability of zero point 0.4. What is the likelihood of someone being in the affected area at the precise time of the release and subsequent event? This can be dynamic, influenced by the operating procedure, shift patterns, or even by the incident itself. For example, operator rushing to the scene in response to the alarm. Let's use zero point 0.5 for the probability of personal presence in the immediate affected area. Given that personnel are present and exposed in the event, for example, explosion or fire, what is the probability of fatal injury? This depends on the specific hazard characteristics, the exposure level, and the worker vulnerability. Let's estimate this as zero point 0.5. Both enabling conditions and the conditional modifiers requires rigorous documentation and ongoing validation to ensure their continued accuracy and the applicability over time. This ensures your LOPA remains credible. Now that we understand initiating event, IPLs, enabling condition, conditional modifiers, it's time to bring it all together to calculate the scenario risk and make informed decisions. The fundamental LOPA calculation for the scenario frequency, considering all these factors, is frequency of the consequence is equals to intermediate event frequency times probability of the enabling condition times probability of the independent protection layer times probability of the conditional modifier. So let's say if you have multiple enabling conditions, for example, then you will have to multiply all those numbers. All the IPLs, you should bring it here in the formula. And similarly for the conditional modifiers. Let's apply this to our continuous reactor example. Initiating event, we know that it is 1 e to the power minus 1, which is loss of the cooling water. Enabling condition is 0.5, probability of the reactor in exotherm phase. Then we have three IPLs. The first one is the operator response, which is 0.1. We have a pressure safety valve, which is 0.001. Then we have safety instrumented function installed with 0.001. Then we have a conditional modifier, probability of the ignition, which is 0.4. Another conditional modifier, probability of the personal presence, which is 0.5. Then the third one is the probability of the fatal injury, which is we have considered 0.5. Multiplying these numbers probabilities together, we will get one number. On the screen, you can see that all the probabilities are listed and we are multiplying it all together. And now the final number is 5 into 10 to the power minus 9. This calculated frequency is then compared against your organization risk tolerance criteria. These criteria define what level of risk is acceptable or tolerable in your operations. For example, a company might set a maximum tolerable risk of 1 e to the power minus 5 fatalities per year for a single scenario. In our case, 5 e to the power minus 9 fatalities per year is significantly lower than this target, indicating that the risk is tolerable and no further action is immediately required to reduce this specific risk. If the calculated risk exceeds the criteria, it signals a need of additional risk reduction measure. This could involve adding more IPL, upgrading existing one, or modifying the process for inherent safety. LOPA helps prioritize these actions based on a clear quantitative basis. Remember, the goal isn't zero risk, which is often an unachievable ideal, but as low as reasonably practicable or allowable, finding a balance between risk and the cost of further reduction. While LOPA is simplified, it's incredibly versatile. Sometimes, for a complex or a high consequence scenario, you might need to go beyond basic LOPA. This is where quantitative risk analysis (QRA) methods like fault tree analysis or event tree analysis comes in. These can provide more rigorous detailed assessment, especially for complex interdependencies or complex cause failures. For instance, common cause failure occur when a single event leads to simultaneous failure for multiple safeguards that might otherwise appear independent. LOPA by default is conservative by often disallowing credit for non-independent elements or eliminating their credits. More advanced QRA can model these dependencies more precisely, providing a less conservative but more accurate risk estimate. Another advanced area is the human reliability analysis, which is HRA, which rigorously assesses human error rates. This is crucially for accurately evaluating human IPLs and human initiating events. HRA goes beyond simple estimate to consider complex factors like stress, fatigue, and the quality of the procedure and training. LOPA utility extends far beyond just accessing single scenario. It's a powerful tool across the process lifecycle, supporting various process safety management elements. LOPA is excellently suited for evaluating the safety impact of modification of the processes and procedures or equipment, ensuring that corporate risk tolerance criteria continues to meet. LOPA is an excellent way to identify safety critical element, those engineering controls that provide independent layer of protection to reduce risk of acceptable level, ensuring that they receive rigorous inspection and maintenance. It also pinpoints safety critical actions, administrative or human actions that act as an IPL, allowing for focus, training, and drill to ensure operator knowledge and the performance. LOPA can inform emergency planners about potential consequence and mitigated frequency of incidents, aiding in a more effective emergency preparedness. It helps assesses risk to occupants in building from potential fire, explosion, or toxic release originating from the process units. LOPA is widely recognized and often specified method for establishing the required safety integrated level for the safety instrumented function, which are the key active IPLs. By understanding these advanced concepts and diverse applications, you can leverage LOPA to build more resilient and safe operation within your organization. And that brings us to the end of our comprehensive LOPA course. We have journeyed from its foundational principle through its core elements and into the nuanced world of the enabling condition and the conditional modifier. We have also seen how IPL served as crucial safeguards and how to quantify their effectiveness. Most importantly, you have all learned how to perform LOPA calculation and use it to make critical risk-based decision, ensuring your processes are as low as reasonably practical in terms of risk. Remember, LOPA is a powerful, semi-quantitative tool that provides clarity, consistency, and the defensible basis for the risk judgment in the complex world of process safety. It complements but do not replace other hazard evaluation methods like HAZOP. Its rigorous yet simplified approach makes it invaluable for managers, engineers, and the practitioners alike. This video is proudly brought to you by Pacific ICS Engineering Limited from New Zealand, where we specialize in functional safety, alarm management, electrical instrumentation, control system, design engineering. Our team of experienced professionals is committed to delivering practical, standard compliant, and industry focused solution tailored to your needs. If you are looking for an expert support in safety lifecycle activities, alarm rationalization, and integrated control system design, we are here to help you. Feel free to reach out to any member of our team. We would love to connect and explore how we can support your next project. Once again, thank you and stay safe.